the seminar. We'll have two presenters today, and Damla can tell us more about the two presenters we have today.
Yes, thank you, Lucas. So I think we are gonna start with Gert, if it's fine for you.
I think it makes sense because I also read already a bit into Manuel's presentation and previous presentation materials from the HW, that it's a good introduction to start with Manuel.
Okay, then let's start with Manuel. Okay, good. So Manuel is a former team member of Swissloop. He graduated last summer with a bachelor degree in mechanical and process engineering at ETH Zurich. He did his thesis on the topic of assessment of heat management strategies for Hyperloop pods. And now he will be present his findings to us. Floor is yours, Manuel.
Okay, so can you hear me?
Yes.
Okay, oh, I need a second to share the screen, but so can you see the screen now?
Yes, perfect.
Good. So, right. So, hello and welcome from my side. As already mentioned, my name is Manuel Kälin, and I did my bachelor thesis, which is called Assessment of Heat Management Strategies for Hyperloop pods. And I did this thesis in collaboration with Swissloop, the Hyperloop student team of ETH Zurich. Good. So I think I want to start with short definition. I think all of you know, or most of you know what a Hyperloop is, but I want to start with this short definition here in bold, and below you can see an example of a Hyperloop pod. So this is the prototype of Swissloop's Hyperloop pod of the season 2024. And on the right side, you can see some technical data. Yes. So my work I've done, I want to do it on a full-scale Hyperloop, and that's why I couldn't take the prototype or the technical data of the prototype to do my calculations, and that's why I had to use a full-scale Hyperloop concept, which is this one you can see here. I think yeah, the most important thing, or one of the most important things, was the temperature and the pressure, the air pressure in the tube of the Hyperloop, and also the geometry of the whole thing, and the cruising speed. I have to mention here that for the temperature, I assumed that I made the assumption here that the Hyperloop tube is 15 meters underground, where the temperature is constant at a value of 12.5 degrees Celsius. And I know probably that's not really realistic, that the tube is underground, but I had to, or it was useful to have a value which is constant to make some calculations and then later to adjust this value. So here you can see the problem I faced in my bachelor thesis. So here you can see this part of the Hyperloop pod is the passenger cabin, and I wanted to or it's important to keep the temperature inside of this passenger cabin at a constant value of 20 degrees Celsius, while heat is generated inside. Here I assumed 4 to 30 kilowatts. Yes, and you can see here that there's also this part here, the motor and the electronics, which I didn't cover in my bachelor thesis because I think it's another or these are two different problems because the motor and the electronics are generating a bigger part of the heat, but also at a higher temperature because they can reach higher temperatures without damage than the passenger cabin where the passengers are located. So I looked in how can I dissipate this heat, and especially I looked at convection and radiation. So I had to solve this thermal network here, and so the temperatures are fixed, and I had to calculate the thermal resistances for convection and radiation, and then after that I can calculate the or I could calculate the heat dissipation and look whether this heat dissipation is in the desired range of 4 to 30 kilowatts or not. I only use part of the surface for the dissipation or for the calculation of the dissipation, also because here this in the lower part there are the motor and the electronics, which are as I mentioned probably at a higher temperature. Yes. So here you can see the two key questions I answered in my thesis, and I will also answer them in this presentation. So the first one is it possible to have enough passive cooling with radiation and convection, yes or no? And the second one is, if no, what can we do to increase the cooling and how much additional power is used for that? So then I begin with the heat transfer through radiation. Here, so I looked for, or we are looking here at this this part of the thermal network, and here you can see the input values I used for calculate the thermal resistance for radiation, and in the blue box that's then the expression for the thermal resistance. And here you can also see that this consists of 3 terms. The last one is basically 0 because this tube surface here is very large, and it's also important to mention here the thermal resistance depends on the temperatures, so on the pod temperature and pod surface temperature and the tube surface temperature. So I could simplify this a bit, and here I added then the second equation to calculate the heat dissipation through radiation. Here is also the thermal resistance in it. Yes. So then I'll go on to convection. Here you can see the temperature curve. So we have here the pot wall on the x-axis, and at the same time that's also the temperature. And on the y-axis, that's the distance from the wall. So here, very close to the wall, we have the same temperature as the pot, and then it approaches the air temperature as it goes to infinity. And then, yeah, here you can see the formulas used to calculate the resistance and the heat dissipation. But now, in the case of the Hyperloop, we have high-speed flow, and there it's a bit different. So here you can see the temperature curve is shifted to the right side. So that's because of viscous dissipation here in this boundary layer close to the pot wall, and because of friction, the air is heated up, and therefore I had also to adjust the equations here. The heat transfer coefficient for convection, and here I replaced this temperature for this equation. The adiabatic wall temperature is used. I will not go into details of the calculation of the adiabatic wall temperature and the heat transfer coefficient, but I can here say to the heat transfer coefficient that I used this correlation of friction and heat transfer because for the friction coefficient, I got this value from a CFD simulation of a Hyperloop pod, and so I thought this would lead to a more accurate calculation. Good. So then you can see here the results of the convection and radiation of the passive cooling, basically. We have about 3 kilowatts of heat dissipation through radiation and convection, and the bigger part is radiation. But because I said in the beginning that I wanted to achieve a range between 4 and 30 kilowatts, that's not enough cooling, and that's why I had to improve the heat dissipation. And one idea to improve was to add fins to the pot surface area here. So the thermal network is changed. The convection part, here we have now this thermal resistance of the fins, and also it has also an influence on radiation because yeah, you can see it here in this formula. The emissivity for the radiation is changed. Yeah, and we also have to adjust the temperature in the equation of the radiation because with the fins, the surface of isn't at a constant temperature anymore, because here on the base it's hotter than at the tip here, and for that this equation here is used. So then here that are the results. As you can see here on the x-axis, that's the fin surface area, also indicated with these green triangles here. And on the y-axis is the heat dissipation. And now it's possible to reach the lower bound of 4 kilowatts of heat dissipation here at the end. So it's the black line here. But also there's also additional friction because we increased the surface area with the fins. So in the blue line here is the additional friction, and that's why this solution is it's not the best solution. And I also thought about other improvements, and this is the heat pump now. So the thermal network is here changed also. So here you have the heat pump, which is cooling the inside of the Hyperloop pod or the passenger cabin. And at the same time, it's heating up the pod surface here. And to describe the heat pump, I used these formulas here. So the first one is the coefficient of performance, which is 60% of an ideal heat pump. Then the second one is an energy balance. And the third is the thermal resistance of the insulation here. So then here again the results. Now for the heat pump, here on the x-axis you can see how the temperature, the pod surface temperature is increased. The heat pump on the y-axis you can see the heat dissipation. And now it's possible to cover this whole region or whole range of 4 to 30 kilowatts of heat dissipation. And for that, 0.6 to 19 kilowatts is used to run the heat pump. So to summarize everything, here again, I have the two questions from the beginning. The first one we answered with no. So the passive cooling is not enough, and that's why some improvement is needed. With the heat pump, it's possible to cover this whole range of 4 to 30 kilowatts. Yes, and the fins are not really a good solution, but there it's also possible to reach 4 kilowatts of cooling power. Yes, and that's also that you can also see this in this table. Yes. So yeah, I want to thank you now for your attention, and if you have questions, then now is the time to ask these questions.
Great, thanks, Manuel. We already have one question in the chat, and that question is looking at other components. So it says, how much do you expect other components of the pod would add with regard to the heat that is needed to be dissipated? And do you think one would use different systems for heat dissipation for electrical components and for the passenger part?
I think I saw also some estimations of values for the heat generation in the in the other parts of the pot. But I have to say that some of these values are really not realistic, I think. So it's not very easy to estimate for me what would be a reasonable value. But I think probably it could be that this problem of the passenger cabin is only 10% of the whole heat that has to be dissipated, or we have to get rid of it in a way. But it's also, as I already mentioned, it's not the same problem, because the temperatures of the electronics, I think they are going to be much higher than the passenger cabin. And to different systems for heat dissipation, I think it depends how long a Hyperloop is running, and there are other ideas as storing or the heat in a thermal battery, and I think probably in the end the best solution would be a combination of different ways to get rid of the generated heat. Yes.
Yeah, maybe also as fail-safe back options that you have in case of emergencies or something else, so that you have other options to get rid of heat. There's another question that came in the chat. I've also put it in the questions. What's the vacuum pressure in the tube with your calculations?
This I mentioned is 1 millibar. Yeah, so that's for the whole calculations. I used 1 millibar.
And then there's a second question that is asked from Nick. He's asking about carrying ice inside the cabin that melts during a journey work. I think he's referring to the phase change that would absorb a lot of the heat.
Yeah, I didn't really look in this specific case, but I know that there are ideas to get rid of the generated heat with thermal batteries, which we work with latent heat storage. Yeah.
Yeah, and I think there have been some proposals already, I think, Nick, that are referring to this, maybe from last year's HW, but you can also take a look at where phase changing materials I think used for this calculations, also similar to the ones you did, yeah. Okay, and then there's a third question from Manuel. You would propose to add a heat pump to increase cooling power. Wouldn't that increase the heat production on the pod as the heat pump itself produces heat again?
Yes, it increases the heat generation, but this is considered inside the heat. I showed the energy balance on the slide with the heat pump, and this is so the power needed to run the heat pump, which generates additional heat, is that I accounted for that in the calculations.
So just increase the difference in heat so that you can dissipate more at a certain time. That's calculated in your energy needs are calculated in there as well. Okay, I don't see any further questions. I think that's it for now. Then we can jump back to Damla to introduce our next speaker.
Yes, sure. It's me again. So yeah, let's continue with Gert. And Gert is a lead engineer at Hyperloop, at Hardt Hyperloop. He graduated with a bachelor degree in computer science at Delft University of Technology. After he worked at the Formula student team at Delft a couple of years, he joined Hardt Hyperloop in 2018. Today, he will be talking about cooling system for a transportation vehicle arranged to be transported in a low pressure environment. Please, Gert, go ahead.
Thank you. Let me quickly share my slides. I'm normally used to Teams, so give me one moment. Should have it up and running in a second. Can you guys see it?
Yes.
Yes, sounds good.
Perfect. Thank you. Thank you for the introduction, Nama. So yes, indeed, quite a convoluted name for the topic I will be presenting. I will probably dive into a bit more simpler terms during the presentation itself. So this has actually been part of a study within Hardt already back in, I think, 2020, 2021, where we analyzed cooling systems for Hyperloop applications, and came mostly to the same conclusions as Manuel just did, that it's going to be very difficult to cool significant amount of heat or transport significant amount of heat inside this thermos flask that we call Hyperloop vehicles. So back in around that time, we came up with this idea that I will discuss in the following slides. So first of all, just to recap, Hyperloop as this mass transit solution, traveling up to or over 700 kilometers an hour, but also, of course, at a lower speed. I did an assessment now at 500 kilometers an hour, which will be probably more like the average speed for routes across a European context. So my work at Hardt, there's actually only a picture here in the bottom right of me at having lunch with the group of guys. But I thought I took some pictures of the more recent work. So over the last few years, we've been working on the European Hyperloop Center and the European Hyperloop Center vehicle. So on the top side, you can see some pictures of the infrastructure as it's being built. And on the bottom side, some of the vehicle, where most of my contributions were on the electronic system of this vehicle and the magnetic system. Other work over the years included different prototypes to test different subsystems. So just a quick look around. So we built in 2020 the static single magnet prototype, which you can see over here, numbered 1. This is basically an XYZ positioning stage to measure and validate the performance of our levitation magnets and propulsion and guidance magnets, where we can measure the forces using force transducers to mostly make our models more accurate for the next development of magnets. Then another interesting one, which we finished in 2022, was the linear synchronous reluctance motor propulsion rig, which is in essence a wheel diameter of around 1 meter, which houses the track infrastructure which we used in the European Hyperloop Center to test also this motor system at higher speeds. Yeah. So why do we need cooling in the first place? Like looking at the different heat sources that we have in a Hyperloop vehicle, I think as Manuel mentioned, we have the passengers and climate control systems, which I took as one of the elements, then the levitation and guidance systems, which contribute to a significant part of the heat as well. Then we have the propulsion systems and the power electronics and battery. Looking at passengers, on average, a seating passenger will emit roughly 100 watts of heat to be cooled. For now, for a 50-passenger vehicle, that would be 5 kilowatts of heat. I counted a factor 2 to 3 to come to total 15 kilowatts of heat for this climate control system. Then looking at the levitation and guidance functions, our magnets that we are testing in the European Hyperloop Center have a power consumption of roughly 0.5 kilowatt per ton, using a permanent magnet to provide the base field of the flux. So scaling that up to a 30,000 kilogram vehicle, that's another 15 kilowatts of heat that we need to dissipate. And guidance, for now, we took an estimate that it would be 50% of the levitation power at 7.5 kilowatts. So that's a total of 22.5 kilowatts. Then for the propulsion system, it's a little bit different. You have the total drag induced by all the different elements in the tube. So a big part of it is the aerodynamic drag, which we estimate to be somewhere around 1,000, like I said here, 700 newtons at 500 kilometers an hour. Then the next element is the magnetic drag, which will be induced by the flux of the levitation magnets changing over time to the steel tracks. For this, we laminate our steel in the European Hyperloop Center, and we intend to keep on doing that because this can give a lift over drag as calculated by the graph on the right of over 1,000. And that means that for this 30,000 kilogram vehicle, we'll experience only 300 newtons of drag at 500 kilometers an hour. Similarly, for guidance, it of course depends on how your infrastructure looks. If it's purely a straight line, then you will have no guidance drag. If you need to do a lot of cornering, you will have induced guidance drag. So here I assume that it's roughly at 1/3 of the levitation drag. Then the total system drag adds up to around 1,100 newtons, or around 150 kilowatts. And then assuming that we can build a propulsion system that is around 90% or above 90% efficient, this means that you will generate another 17 kilowatts of heat on board from just the motor system alone. Then we take another 90% compounding efficiency over the total energy consumption, which will add up to another 22.5 kilowatts of heat generated in the systems. So looking at the total picture, we get to, in this theoretical case for this Hyperloop vehicle, 50 passengers, around 80 kilowatts of heat that needs to be rejected. So the next question is, how would you cool this? So as Manuel said, convection cooling doesn't really work. Radiation cooling, you need to either boost the vehicle's surface temperature or cool the tube or cool both. Otherwise, you again run into trouble when the tube heats up. Then another system often coined for these kind of applications is PCM, paraffin wax type thermal storage, which does around 200 kilojoules per kilogram. It's quite volumetrically efficient, so it should be quite doable to package that. However, you need another 10% of mass, assuming this already good case for a 1,000 kilometer trip, which would mean for a 2,000 kilometer trip, it doubles, of course, but also if the estimations on the drag are off by a factor 2, which they could very well be, that would also mean another doubling. And additionally to storing the heat, you get a big problem if you need to get rid of this heat again. So instead of removing the heat over the entire course of the 1,000 kilometers, a little bit, you store all this and then you dump it in the stations where all these vehicles would either need to swap these PCMs, and maybe you could use it for different heating purposes in city center or some solution like that, but it does require a significant amount of additional systems that you would need to use to then cool this down again. So back in 2019, I was watching a YouTube video from Smarter Every Day, and I guess I became a bit smarter that day. And it's about the Saturn V and specifically the instrument cluster of the Saturn V. There they mention that they use in space applications, they use sublimators. And sublimators are basically leaky radiators where you put water in and the water will freeze, closing the sublimator, but then under the presence of vacuum and the presence of additional heat coming from this system, you will force the ice to turn into water vapor. And this water vapor then takes a bunch of the heat you generated along with it. What is interesting is that you do require a feed water storage. So you do have a system. However, it's in liquid form. So in stations, you could easily refill it when docking. Then, other use cases where it was used. So for example, here in the Saturn V, but also in the lunar module and in some other smaller short trip space missions. So the sublimation energy per kilogram is around 2.86 megajoules. So this again is around 10 times, more than 10 times better than the energy you can store per kilogram in a thermal battery. Also around 10 times better than taking on ice and freezing it or letting it melt. Then you add up to around 400 kilojoules per kilogram. And then you have the problem again of getting a solid substance on board through a vacuum. So we can utilize the same sublimator because at 1 millibar, we are quite a bit below the triple point of water. So in this tube environment, if kept at 100 pascals, water vapor will only exist either as ice or as a gas. Using this calculation of the 2.86 megajoules, you will add up to around 200 kilograms of water that you would need to take on board instead of the more than 3,000 kilograms of wax. So common systems, just to calculate a bit with how much extra mass do we need to add in the sublimator itself. So the sublimator, as a design example from NASA, from the X-38 sublimator, it has roughly a performance of 1.2 kilograms per kilowatt. So also this for the steady state cooling of 77 kilowatts would only be 93 kilograms of sublimator mass. However, in space, you have space. You dump all your water vapor just in the vacuum of space and it will not increase the pressure of space. Well, it will, but ever so slightly, that it doesn't matter. However, if you start doing this in a pipe environment, we'll of course quickly run into issues in terms of the amount of pumping power we would have to introduce. So this is a quick overview of the system as drawn. So you have your pipe, you have a pump on board in this case, it's drawn as a single loop where you could either sublimate water away from your reservoir or run it in. And here you have a heat exchanger with the rest of your heating systems. And then just to indicate the vacuum condition to supply this 1 millibar environment. So if we would indeed pump it out, one vehicle, not that big of a problem. However, if you're transporting a lot of passengers, 10,000 passengers per hour, I'm using in this example, you're looking at 200 vehicles per hour over this 1,000-kilometer trip. And then they introduce in each kilometer 40 kilograms of water. And this is where it starts to become already a little bit more of a problem. So we would introduce 54,000 cubic meters of gas at 1 millibar. And if we look at commercial vacuum pumps, for example, this one is the Roots pump that we used to evacuate the European Hyperloop Center. It does around 14 cubic meters per hour at this 1 millibar. So you would need at least 40 of these pumps and the backing pumps required. So then you would start to look at a megawatt per kilometer of additional pumping load, order of magnitude. However, also here seems to be a solution, and that is freeze drying, or comes from the industry called freeze drying, where in essence the Hyperloop vehicle is this tray of strawberries or other fruits. So instead of pumping it out, we condense the water vapor again, thus keeping an equilibrium between the water vapor introduced by the vehicles and condensed again on these condensers. So a freeze dryer is in essence a combination of a vacuum tube, often at below 1 millibar pressures, food that is frozen, heated plates to introduce the heat, that's our waste heat that we try to reject, and then a condensing system where this water vapor can sublimate out of the goods, leaving dried goods behind. As I said from the triple point, there is no water, liquid water, and liquid water is what gets products mushy. So in essence, it is as if it behaves similar to dry ice in these conditions. So how would that roughly look? You would place cooling tubes in chambers next to the tube, added to the tube. And once you cool them below the point where you start to condense your vapor back to ice, you start building up ice on these cooling loops. If you consider an environment where the air has a certain vapor pressure of water vapor introduced in the pipe, this will of course cause a pressure drop near the condenser where it removes this pressure again, and then induces a flow, a pumping flow as it were, to remove this water vapor towards, or move this water vapor towards the condenser. There's a lot of this is, by the way, based on a book about freeze drying, where they go into the detail of how you should size these systems for freeze drying, where the interesting difference to a Hyperloop system is that we operate, can I move this? We operate more at the 1 millibar level. So we operate at relatively high vapor flow densities, irrespective of blockage ratios, in essence, to the condenser. So you would still need to optimize this to some extent to minimize the path the flow has to travel to reach the condenser. That could be by distributing the condensers along the infrastructure, or making sure that you have enough flow towards these. Nevertheless, at this 1 millibar, you can expect vapor flow density values of 30 grams per hour per square centimeters. So the other part, of course, you will need this -30-degree liquid inside these tubes. And it's important that you apply this cooling power to this liquid so that the liquid won't heat up. And another important aspect here to take into account is that, of course, the temperature gradient across these pipes should be relatively low so that you ensure equal ice growth across the total condenser surface. One more element to take into account, that the ice is also an insulator, especially if it would have mixed with some permanent gases and grow a certain snow ice. But as a rule of thumb, you should not let more than 1 centimeter of ice grow on the surface area of the condenser. And then once this is reached, you need to defrost it again. So the energy required for this process to condense is again roughly equal to the heat of sublimation. So in essence, you are effectively moving heat now from a problem on the vehicle to a problem on the infrastructure. And next to that, you of course then need to provide energy to do this condensation. This condensation, from literature, it also shows different pumps that for freeze drying, often you need to go to quite low temperatures because of the higher pressure, the lower pressure they operate at. But at our pressures, -22 degrees is the triple point. So assuming somewhere between -30 and -40 degrees, you can expect that you can design cooling systems, refrigerating systems that exceed an efficiency of 2. That means for the total system, you would need around 7.7 kilowatts of electric power per kilometer to be able to supply this cooling need. Then to close the loop for a calculation example, if we indeed have these 10,000 passengers per hour, we would only need for these 40 kilograms around 0.13 square meters of condenser surface area to generate this flow area. And even if that vapor flow is restricted by an order of magnitude, it's still only 1.2 or 1.3 square meters of condenser surface. However, the more stringent requirement is the surface area of the ice built up. So one can calculate with the density of ice that 1 square meter has only around 9 kilograms of capacity of ice before you need to defrost it again. So you would need at least 4.5 square meters or 5 square meters of condenser area per kilometer of tube to meet this requirement. And then from the fact that half are probably defrosting while the other half are cooling or condensing, you need to double this again. Yeah, that's in essence it. Just to summarize. So with a combination of space technologies and food processing, we seem to arrive at a cooling system suitable for rejecting large amounts of heat inside this vacuum environment. As shown, for 1,000-kilometer trips, an additional mass is required at less than 5% of the vehicle mass. It's more around 2.5%, but I try to be a bit more conservative here. Even at these 10,000 passengers per hour, the total condenser capacity is only 10 square meters per kilometer. And the refrigeration cycle together with this condensing can reduce the total power capacity needed to realize this vapor requirement from 8 kilowatts to or from 800 kilowatts to 8 kilowatts. Then I wanted to still list a few research topics. At this stage, also within Hardt, this is purely based on calculations and literature research. We still are to build prototype tests to validate these sublimated calculations for one, but also prove indeed this heat flow would be able to be done rather efficiently. Another interesting research topic is, I think, the vapor flow and how it would actually behave. What kind of effects does this have on the total efficiency of a Hyperloop system? You could imagine that you need at least a partial pressure of water vapor in your system. So that means either pumping down the tubes below 1 millibar to get to equivalent pressure of 1 millibar, or allowing to run at slightly higher pressures, thus increasing the drag figures again. Additionally, the condenser defrosting system, there's probably clever ways to make this more efficient altogether. And then finally, hopefully we can at some point make a demonstrator capable of continuous cycling throughout European Hyperloop Center or similar test facility. Then, as the last closing remarks, I didn't account here for accelerating and braking. This will increase the total heat generation significantly if a route requires so much acceleration and braking. An additional improvement, if the acceleration and braking seems to be a large heat generator, would be to move a motor system for at least parts of this journey off-board, which could reduce this cooling requirement again. And as you've seen, the system scales significantly with drag, so better drag estimates will be required for correct siting. That's it. Thank you.
Great, thanks, Gert, for the very interesting ideas there and the nice estimations. I think it's always nice to see some values to really look at and to get an estimate of what kind of heat outputs we have and where we can disseminate that heat. So we have two questions already, three maybe. First of all, the power consumption of heat dissipation values you presented are looking quite optimistic for Manuel. Are you able to validate these assumed values by the EHC or with any experiments you did already?
Currently, to some extent. For example, the levitation power consumptions are based on analysis from the magnetic modeling together with the dynamic behavior of a vehicle flying through that is a combination of the magnetic modeling and as well as the dynamic modeling, estimating what kind of powers we need to keep the vehicle stable at these different forces.
Yeah. So there's some underlaying values, I think, that you can really rely on there.
Yeah, I think one takeaway there is also that they need to be more detailed, and if the drag values increase significantly, the system increases significantly. But I feel that even with those figures, it seems that even if it's 100 square meters of condenser surface area per kilometer, that would still be a feasible amount of condenser area.
And that is already including the doubling because of the defrosting and frosting?
So I took now for the cooling of the condensers, just the cooling, keeping the coolant. If you defrost, you can probably use the atmosphere to your advantage by either running a much more efficient higher temperature coolant flow through there, or other ways to defrost it by exposing it back to the ambient air and draining it as a liquid. But it's not included in this figure now.
Okay, so the process of defrosting is also not included in the energy estimation, or? Okay, so yeah, that was the second question. In the 7.7 kilowatts per kilometer, there's the efficiency of the condensers and the defrosting and frosting in there. If it's both phases and the figure 2, I think
so that's only
you said in
phase.
efficiency.
That's only the cooling
Single
alcohol.
phase.
But I think, so as I said, I feel that with the defrosting, you can probably implement a rather efficient way of rejecting it to the heat, to the environment without introducing a lot of power.
Yeah, depending where you are going, probably with the Hyperloop and what the outlet conditions are.
Yeah.
But yeah, then there's another question from Nick again. How would tighter, so probably a lower vacuum, change things? Say, for example, 0.001 millibars. That I think.
I think.
Well, maybe you'll answer on that.
Yeah, so I think, of course, the drag would come significantly less. What we saw in some externally validated aerodynamics figures is that they scale roughly linear still with pressure. So this would be 1,000 times lower pressure. I think your vacuum pump energy consumption would be through the roof. At the same time, you do see that the vapor flow density decreases. So if you don't account for any means to reduce your magnetic drag to get that lower as well, just lowering pressure for aerodynamic drag will probably actually make this concept more difficult to achieve.
Yeah, I think you had a very nice graph of the different levels of the energy that is consumed in the vehicle, or the heat that is needed to be dissipated in the vehicle. So I think if you look at that is quite a nice.
In essence, only the propulsion goes down with lower aerodynamic drag, but the rest would stay, and also the electronics and battery. So these would become, let's say, best case 10 times less. Then you still only achieve a halving of your total heat reduction. But if you look at the other graphs, you're suddenly at a vapor flow density somewhere beyond the graph. Or wait, in pressure, I think again still beyond the graph, where you will gonna have very low vapor flow, and that vapor flow will then means that you can't transfer as much heat. So you need a lot more condenser surface area than you would at these higher pressures.
Yeah, and I think, as you said, and as those two figures show, like reducing one in an order of magnitude doesn't help you because the other one doesn't do as well. Then I think Nick just re-asking maybe smaller tubes, and maybe you can re-explain. I think the graph was quite nice, but maybe you can re-explain what effect the water vapor has on the aerodynamics of the system.
Yeah, so as I said, the water vapor can be seen as simply seen, at least on the molecular level. There are different effects happening, but simply seen as an increase in pressure. So to be able to move a certain mass flow, you will need to have a certain pressure difference. So this will account as a certain vapor pressure of water. I have some. Let me quickly try and open the book on the freeze drying, where they have an example. Now I need to find it. I think we are about there. You can see a pilot plant for freeze drying, where they sublimated 25% of 300 kilograms over the course of 3 hours. And here you can see that the pressure difference between the condenser and the chamber has roughly a pressure difference somewhere below 0.1 millibar. So you can expect that at 1 millibar, your pressure would need to go up to, let's say, 1.1 millibar to allow for sufficient vapor flow. But probably this can be offset more efficiently by going down a little bit. The 1 millibar versus half a millibar might still be worth looking into in terms of efficiency figures, of course. But that's, yeah, there's a lot of optimization in the whole system. These aerodynamic figures come mostly from an assumption of a 3.5 meter tube with a 2.5 meter vehicle. Again, aerodynamics are now reasonable at these 500 kilometers an hour. Of course, at 700 kilometers an hour, it's already more. So you would encounter that you would, for 700 kilometers an hour, need to probably take significantly more water to overcome these drag figures. You can probably expect that you would have twice the propulsion losses and battery losses at these higher speeds. It would roughly be a similar trade-off if you go to a smaller tube and a higher blockage ratio.
Yeah, and then also I think Nick asked about very much lower pressures. So if you go down to not only 2 millibar or 0.1, but a lot lower, I think that requires other pump technology. So
yeah,
that would
then you're
also increase your energy.
Turbomolecular pumps, I think, for these kind of pressures. So that makes already for unfeasible amounts of power. But depending on
your
the
pump technology needs a lot more power, yeah.
A bit lower than the 1 millibar already.
Yeah, but not too much, as we would say for that one. Okay.
Yeah.
I hope that answers all the questions. Perfect. I see a thumbs up. That's good. And I think then that is all the questions we have. I would say very thanks to you both, the presenters of today's